1.3, from the chemist's viewpoint, the most interesting characteristic of an atom is its ability to combine with other atoms to form compounds. The forces that hold these atoms together are called chemical bonds. We should know this already, right? Right? Awesome. So one type of bonding is covalent bonding, and that is by the electrons being shared. Sharing is caring. These bonds are called covalent bonds, and they form molecules. Molecular compounds are sometimes called covalent compounds in our book. Molecules can be represented in many different ways, but the simplest way is a chemical formula. This involves the elements, symbols, and the relative numbers of atoms. Excuse me. For example, anybody know what the picture A is called? Lewis structure. Yes. This is called the space filling model. It's the same thing, but it's just like giving a spherical shape to each atom. And then this is a ball and stick model. I think we're going to build some with this year, just to see more bonding and that kind of stuff. Mr. F apparently has a lot of kids, so I'm going to steal them from him. So all my Chem 1 students said that he has them. So ionic bonding is the other type of bonding, and this involves attraction between ions. An ion, remember, is an atom or a group of atoms that has a positive or negative charge. And a positive ion is called a cation because it loses an electron. So I know it's kind of hard to see in this picture, but sodium will lose an electron, and that will turn into the sodium ion. So, review, right? We all know this. So, and if an electron is gained, it's called an anion. Some people thought of them as onions in Chem 1 because they didn't like onions. Opposite charged ions attract each other, and this is called ionic bonding. We know that. A solid consisting of oppositely charged ions is called an ionic solid. Ionic solids can consist of simple ions or polyatomic ions. I need to get you guys that list. Sorry. Just in case you need it for polyatomic ions. But there are some listed in your packet too. So we're going to get there. So we're first going to review how to write formulas and name compounds. Binary compounds are those that consist of two elements, and they can be ionic or covalent compounds. So here I have a bunch pictured, like H2. Remember the diatomic molecules have punctal fiber. Are molecules that have the same element, and then you have other molecules that don't have the same elements, and those make molecular compounds too. So to write ionic compounds, names. The cation is always named first, and the anion is always second. A monatomic cation takes its name from the name of the element. Do you guys know what monatomic means? One atom. Yep, mono is one. A monatomic anion is named by taking only the root of the element name and replacing it with "ide," something we did in Chem 1. And then the polyatomic ion, you just use the full polyatomic ion. Okay? For covalent compounds, or molecular compounds, as we call them in Chem 1, these are formed with two nonmetals, and the first element is used, the full element name is there, and then the second element is named as if it was an anion, so you change it to IDE. And these prefixes are given. If you flip over your notes, or if you're already flipped, I give you a bunch of stuff. I give you a bunch of tables. So I don't have them up on the screen, but on those tables, I have some common monatomic cation anion names, some common cations that have multiple charges, because they are probably in the transition metal group. So then we would use a Roman numeral for them. I have the prefixes listed there, and on page 6, there's also a bunch of common polyatomic ions for you as well. Okay? So I will get you another list that's just like a half sheet of paper for polyatomic ions too, but this is here for now because I forgot. Sorry. Okay, so we're first going to practice naming these. Do we want to go fast? Want to go slow? What do you want to do? It's all mixed together. Medium pace, fast pace. Okay, Well, first of all, the way that we name them is based on if it's ionic or covalent bonding. So the first one, Fe2O3, would that be ionic or covalent?
I forget how you tell it.
It's the way you tell the difference. Ionic includes a metal usually, or a polyatomic ion. So what do you think for this one? It's ionic. Yep. I'm going to just write an I so that we remember it's ionic. So you can look back in the instructions if you need to. When it's ionic, the first name is the name of the element from the periodic table. So what's Fe called? Iron. And then the second, if it's not a polyatomic ion, we change the ending to I. So that would be oxide. Now, this is a trick question. Why? Because iron is in the central located part of our periodic table. It is a transition metal that can have two different charges, and so we have to use a Roman numeral to see the charge. What's the charge of it? Is it a 2 or a 3? It's a 3. Remember, this is the charge of that one. So we would put a Roman numeral 3 after the word iron. So the correct name would be iron 3 oxide. Okay, do you guys want to go? Okay, I know what we're doing. Okay, AlCl3, ionic or covalent molecular? Ionic, because aluminum is a metal. What's the name of this one? Is aluminum in the transition metal spot? No, so we don't need the 3 on this one. It's just aluminum chloride. That's it. Next, is lithium a metal? Anything on the left side of the periodic table is metal, so lithium is a metal. So this is ionic. Okay, somebody take a guess. What's LiH called? Lithium hydride. It doesn't have an O, so it's not hydroxide. So it's just hydride. And in Chem 1, whenever you would see hydride, or you'd have to name hydride, it really threw everybody off. So I threw this on here just so that you see that is an option. What if it was hydroxide? What would it need included? An oxidant. Yep. Okay. Next one up the top. KH2PO4. This is ionic because if you look at the table of polyatomic ions, the H2PO4 has a special name, and it's not something you had to know last year in Chem 1. So what's the name of that? Dihydrogen phosphate. So we're going to use dihydrogen phosphate for the second part of the name, and K is potassium. So it's potassium dihydrogen phosphate. Potassium dihydrogen phosphate. So, yes. In this bottom drawer. Okay. I only had you guys know, I think, so I don't remember how many, like 20 or something polyatomic ions. There's a lot more. We just didn't touch over all of them. And Chem 1. Okay, next one. PCl3. Does it contain a metal? Or a polyatomic ion? No. So what type of bonding is it? Covalent. So or you could call it a covalent compound or a molecular compound. Okay. So when it's covalent, you use prefixes to tell how many, except for the first one. If there's only one on the first one, you don't have to put mono in front of it. And if you forget what the prefixes are, there's a table on page 5 in your notes. Okay? So what's the name of this? Phosphorus trichloride. You still change the second element's ending to IDE. That's why chloride is correct for that part. Okay? And then SO2, is there a metal or a polyatomic ion? Nope. So this would be also covalent. And that would be called?
Sulfur dioxide.
Sulfur dioxide. practice with this with the naming. I do have some worksheets that I could print off from Chemistry 1 that wouldn't be for a grade, but for the homework on this section, there's a few problems that you do practice this as well. But if you find that you need more practice, I have some extra stuff to give you. Or I could even print, or I can add to It's Learning the videos from Chem 1 that go into more detail about all of the rules with naming. So if anybody needs that, just let me know and I can get that stuff for you. Okay? So then, after naming practice, let's practice writing formulas. If it is ionic, we will need to look up their charges and then balance the charges to 0. If it's covalent, charges don't matter. You use the prefixes to show how many for that direct element. Okay? So the first one, potassium iodide, is that ionic or covalent? Ionic, because potassium is a metal. Because group 1A are metals. What's the charge on potassium? +1. And the charge on iodide? What is iodide? Iodine. That was one in Chem 1 that people would get messed up. So on your periodic table, if you need to write down the charges from the columns, like we do in Chem 1, you are more than welcome to do that. Okay? 1A are all +1. Iodide is in 7A, and those are all -1. So the formula for potassium iodide would be Ki. Okay, next one, we have gallium. I don't know if we've ever used gallium before. Does anybody know the symbol of gallium? Ga, yeah. So this is one that if you have your periodic table without names, you just want to kind of guess, and it's either going to be the first or the first and second or the first and third letters for the symbol. So gallium is Ga. Is that a metal? Yes, it's on the left of the stair-step line, so it is a metal. So this is ionic. Okay? Gallium, if you haven't found it yet, it's underneath aluminum. So what's the charge on aluminum? +3. So gallium has a +3 charge. And bromide is -1, Br -1. So how do we write the formula for that? GaBr3. So just to refresh, since it's -1 and the charges have to add together to equal 0, we have to triple the number of bromides to make that happen. Or if you remember like the cheat way of crossing, that's fine too. Okay? And if you need help on that, I can help you. Okay, next one, cesium perchlorate. Cesium is another one we haven't used very much. Which one is it? CS. Okay. Is that a metal?
Yeah.
Yes. So it's ionic. And what's the charge on cesium? +1. It's in the group 1A metals. So it's +1. And perchlorate, a hint to know that it is a polyatomic ion, it has per in front of it, and it ends in ATE. ClO4 -1. Okay, so that would just be CsClO4 because the +1 and the -1 cancel each other out. Okay? Other side, lead 2 chloride. It is ionic. Lead is Pb. Guys are remembering peanut butter. Okay, and the Roman numeral tells us what? +2. Not that there's 2 of them. It's telling us it's a +2 charge. Okay? And then fluoride is a -1, so that will be PbCl2. Okay? Sulfur hexafluoride. It has hexa in it. So that's a hint that it's going to be covalent. Or, if you looked for sulfur and you looked for fluoride on the periodic table, they're both to the right of the stair-step line, so they are both nonmetals, so that would make it covalent. Okay? And the prefix tells how many. So how many sulfurs? 1 sulfur. And then how many fluorines? 6. I wrote 5 because you said 5.
Wait, what's 5?
Penta.
Oh, okay.
Penta. Hexa is 6. So SF6. Don't put FL. Okay. And last but not least, tin 4 oxide. If it has a Roman numeral, like what kind of bonding does it have? Ionic, because the Roman numeral only goes with metals, and metals are anionic. Okay, so that's a hint for that. What's the symbol of tin? No, that's titanium. SN. This one is one of those Latin-based ones, and it is SN for stannum. And then the Roman numeral 4 tells us +4 charge. And what's the charge on oxide? -2. What do you think the formula is? The correct response is the reduced way, because if you didn't do the crossing and you just looked at the charges, you would just need one more oxygen to balance out the charge. So it's technically SnO2. I did this on purpose to give you a tricky one. If you were to put SN2O4, that is not an empirical formula, so you would just reduce it down. And you can reduce it because they're not polyatomic ions, so it could change. It's just a tricky one if you do the crossing primarily. Back to chemistry. There are some fundamental chemical laws that we need to discuss that you will need to know for the AP exam, which we have talked about briefly in Chemistry 1. The first one is the law of conservation of mass. Antoine Lavoisier, he's a French guy, used combustion to determine this fundamental law. He carefully weighed out the reactants and products of various reactions that were kept in a sealed container. And then he was able to see that because it was sealed, nothing was able to escape, and it weighed the same before the reaction and after the reaction. But before he put it in this sealed up container, they thought that you lost mass. Because when you combust things, products are usually gases or in gaseous form. So they thought they were losing mass, but really they were just losing gas into the room. So this was the first time anybody came up with that. So this law suggests that mass is neither created nor destroyed in a chemical reaction. So that must be Antoine Lavoisier. And that's somebody. Okay. The law of definite proportions came from Joseph Proust, where he was taking careful weight measurements and found that a given compound always contains exactly the same proportion of elements by mass. So this is difficult for people in Chem 1 to figure out compared to the next one. But definite proportions is just basically saying that if you have water, the formula is H2O. Okay? If you changed it and it's not H2O, 2 hydrogens for 1 oxygen, then it is no longer called water. So that ratio of 2 H's for every 1 O is what definite proportions means. Okay? Multiple proportions. So when things react, you get the same parts over and over. Okay, whatever. So John Dalton came up with multiple proportions, where he said, okay, yes, you guys are both talking about the right thing, and both your findings are correct, but sometimes elements form different types of compounds. So, like if you throw in some nitrogens and oxygens, you can create different compounds based on that. So, for example, carbon and oxygen can form 2 compounds, carbon monoxide and carbon dioxide. So they contain the same elements, but the ratio is different. That's the difference between multiple proportions and definite proportions. In definite, the ratio stays the same. In multiple, the ratio is different. Okay? Say that again?
That's a period.
It's a period.
I thought it was
Okay.
minus.
To summarize his finding, Dalton found that when 2 elements form a series of compounds, the ratios of the masses of the second element that combine with 1 gram of the first element can always be reduced to small whole numbers. So we're going to see this in example 7. Okay. Where we want to show how, if you, because he had mass data, and so the reason why they proved this law is using mass data. Okay? So if we have compound A, compound B, and compound C, that we know these compounds only include nitrogen and oxygen, we want to show how these illustrate the law of multiple proportions. Okay? So let's divide, shall we? So let's just take the first 2, A divided by B, and see what we get. A is biggest, right? Okay, so 1.750 grams divided by 0.8750 grams. anybody have their calculators? Sorry. This is the only math for today. Two, exactly. Okay. So you could say sometimes ratios are written like 2/1, right? If it's simplified. So there's twice as much mass in A as there is B. Everybody agree with that?
Yes.
Okay. Now let's compare B and C. So if we take B on top because it's bigger, divided by C, the 0.8750 divided by 0.4375, what do you get? Same thing, 2 again? Okay, so B is twice as big as C. So if A is twice as big as B, and C is twice as big as, or B is twice as big as C, what do you think the ratio is compared A to C before we try it? 4 to 1. Okay, let's just prove it to make sure. If we take A divided by B, so 1.750 divided by 0.4375, is it 4? Yeah. Okay, so these ratio numbers are what Dalton did to help prove that the ratio of the masses can always be reduced, and if they have the same elements in them, then you can, what is that property in math class when it's like, if A plus B equals C, and this and this and this, and then transitive property. Thank you. Kind of like that. Oh, look at that. I had so much room for me to work on. Okay, using the data from example 7, we can apply the findings to compounds composed of nitrogen and oxygen. So, one situation we could say is that, because it was, this is 4 times as big as this, and twice as big, we could say that a compound would have 2 nitrogens for every 1 oxygen. And then if we simplified that down by half of the number of nitrogens, we would have 1 and 1 for B. And then if we had to be 4 less with this, it would turn into 1 nitrogen and 2 oxygens. Okay? So those are 3 different formulas for compounds that could fit this ratio set. Okay? Depending on the 2 to 1, the 2 to 1, and the 4 to 1. Okay? Another option, now do you need to write this down? I don't know. But another option could be with this whole ratio situation. If we put A as 1 to 1, then for B, we have to double the number of oxygens. And for C, we would have to make it 4 oxygens. And that would still fit the same ratio of what we had figured out mathematically. Okay, so this is just saying that back at the time, Dalton didn't know what exactly were in his samples of nitrogen and oxygens, but these are possible variations of that, what it could have been. Okay? And one more set, just in case you wanted to make things more complicated, you could have 4 nitrogens for 2 oxygens, which you would reduce down the number of nitrogens, or you could have 2 nitrogens and 4 oxygens to fit this same ratio again. Okay, so as you can see, infinite possibilities exist because we could just continue to increase A's number of atoms and then go from there to figure out the ratio. So that's what Dalton worked with. Okay? Now, how do we determine the formula of a compound? We do this by decomposing a weighted sample into its component elements and then finding the mass of each compound. So this is a picture of what you could do where you heat up a sample and then it breaks apart into its products or its smaller compounds, and then you can weigh each part, and then theoretically each part would add up to the whole because of the whole conservation of mass law. Okay? So with this, we have found that we have empirical formulas and molecular formulas. Empirical formulas are the smallest whole number ratio, and a molecular formula has the same empirical formula, but the molar mass is bigger. So maybe it's double the empirical formula or triple the empirical formula. So I have some pictures here that show this. So C6H6 is called benzene. And the empirical formula would be CH, because you just divide the two subscripts down. And so the C6H6, the benzene, is 6 times the mass of the empirical formula. Sulfur is sometimes in the formula of S8, because 8 atoms of sulfur stick together. And so that empirical formula would just be sulfur by itself, and then the mass is 8 times as large. And then C6H12O6, what's that called? From biology. Glucose. You can find the empirical formula there, and that means the mass is 6 times as big as that. Okay, so to find the empirical formula, we did this in Chem 1. The steps. My simplified steps are there for you. And the poem is percent to mass, mass to moles, divide by smallest, round to whole. What do? Percent to mass. You are given percentages, you change it to grams. Okay? Mass to moles. How do we did this yesterday. How do you go between grams and moles? What do you use? If I have 12 grams, you molar mass. Yep. So you're going to divide by molar mass. I'm going to put mm for molar mass of each element. So if you have carbon, oxygen, and hydrogen, carbon's mass gets divided by carbon's molar mass. Hydrogen gets divided by hydrogen's molar mass. Okay? You don't use the full molar mass of all of them together. After that, you're going to have numbers, and you just divide by smallest. You are creating a ratio so that one of them is going to be a 1 at least. Okay? So just out of your mole answers, then you divide by the smallest, and then you round them to whole. So if it's like 1.99, rounds up to 2, they should be a whole number. Now, in Chem 1, I took out the hard things when it's like not a whole number, but it's like 1.5. In AP, you have to know what to do with that. So you have to get rid of those decimals if it's not a perfect rounding number. And the way you get rid of that is if you had like 2.5, you would multiply everything by 2. And then that would increase everything by 2, multiplied by 2, but then that would make that an even number. Or if you got something like 1.67 or 1.3, anybody want to take a guess what you multiplied by? 6.67 would be what fraction? 2/3. So we would multiply by 3 to get that, a whole number. Okay? So you're gonna see that more here because that is harder than Chem 1. So determine the empirical formula for a compound that has the following percentages. So the first step, we do mass, percent to mass. Okay? So when we did this in Chem 1, we would keep all of our elements separate. So we have chlorine, we have carbon, and we have hydrogen. Okay? So percent to mass, just change the percent sign to a gram sign. So that is the first step in the poem. Second step is mass to moles. So we will divide by molar mass of each element. And I don't care if you use what's on your periodic table or if you have one memorized. Either is going to be fine. To save some time, if you could find one and then just tell me which element you did, and then I'll write down your answer. So we'll divide this and conquer it up. Those who have calculators.
Last one is 4.02.
0297? Okay. 2 point. It should be,
Yeah.
the CL and the C should both be 2 something. Okay, I'll just cut it there. Okay.
The second one's 2.020.
Oh, that's what.
Okay, so these, we have changed them into moles. The next step is divide by smallest. So at this point, you look at the numbers you have, and what's the smallest number? 2.02, right? So we're going to divide all 3 numbers by the 2.02 number. Now, we need to round it to whole. So if we have 2.02 divided by 2.02, that's going to be 1, right? And then is the C, the carbon, also going to be 1?
Yep.
Basically, because we got to round it to whole. And then what about the hydrogen? What's that going to be? 2. So now, remember, these are not the final answer for empirical formula. These are the subscripts that you put on the elements to make the formula up. Okay? So the formula would be Cl1, C1, H2. So this is the empirical formula for our compound. Remember doing this?
Yeah.
Chem 1? Okay. It's just a lot of steps. I think in the homework is when you have those crazy ones where it's like half or a third. And maybe tomorrow we could do one of those really quick at the beginning. Okay. After you know the empirical formula, then to find the molecular formula, you just do a comparison of the molar masses. Where if I want you to find the molecular formula, I'm going to give you a molar mass in the problem. And so you take the molar mass of the compound in the problem, divided by the empirical formula's molar mass. So we would find like the ClCH2's molar mass and plug that in. And then whatever that ratio is, that number, we multiply the subscripts by that number to create the molecular formula. Okay? So based on what we have in example 6, where our compound was ClCHOH2, we want to know the molecular formula if the molar mass of the compound, the molecular formula compound, is 98.96. Okay? So we're going to take the 98.96 divided by the molar mass of ClCH2. Okay? So, can somebody tell me what that molar mass is? Or do you want me to just do it because we're going to be done soon? I got this molar mass to be 49.48. Okay? So then the molar mass of the empirical will go in the denominator. If you need to make more notes than this, you can. I'm just trying to simplify time. Okay? And when you divide them out, it's going to round to be about 2. So then, to find the molecular formula, all we do is we multiply each of the subscripts in this guy by 2, and that's the molecular formula. So that would be Cl2, C2, H4.